Welcome. Today we have a very interesting subject to cover. It's called cold fusion, fiction or fact or fiction. Either way you can look at it. And I have two very interesting gentlemen next to me. This is brought to you by the Knights of Columbus, the St. John de Matha Council 5564. It's located in Hyattsville, Maryland, and the Michael J. Curley Assembly. My name is David Pittman. I'm the moderator here. And to my immediate left is Scott Chubb and Talbot Chubb. And they have quite an interesting story to tell. They've been involved in studying cold fusion for quite a few years now, and they have quite a background to tell you, to explain how they got interested in this and how it's progressing today. So I'd like to introduce Scott first. Could you give us a little bit of background on yourself, and then Talbot, give us a little background on yourself so the audience can see exactly why you got interested in this subject.
Yes, I majored in physics at Princeton University, and after that I went to the State University of New York at Stony Brook, where I got my PhD in solid-state physics. And then after working as a postdoctoral fellow in several places, Northwestern University and at the Naval Research Laboratory, I became a permanent research physicist at the Naval Research Laboratory, where I've studied numerous things ranging from precision time and space, remote sensing of the ocean from space, and solid-state physics, the electronic structure of materials. My involvement with cold fusion reflects the fact that I saw very early on that there were potential possibilities that most people had not thought of. In particular, when I was at Brookhaven National Laboratory working as a graduate student, I became intimately involved with the materials, the palladium and hydrogen interacting with palladium, that Pons and Fleischmann worked on and was the basis of what they were doing. And it occurred to me early on that the way that most people had been thinking about cold fusion, which is in terms of conventional hot fusion, really was a mistake. That hydrogen and metals can behave, when hydrogen goes into metals, it can behave in a very different way than people were thinking about, and as a result, very unexpected things could happen.
Talbot, how did you get together, and how did you have a common interest in this?
Well, I also went to got my undergraduate degree from Princeton in physics, and went to worked on the atomic bomb at Oak Ridge, Tennessee, during World War II, and then went to the University of North Carolina and got a degree in experimental physics, and then joined Naval Research Lab and worked in the space program under Dr. Herbert Friedman for about 35 years. And so I continued to be associated with NRL when Scott joined the organization. And like all physicists, everybody was very intrigued with cold fusion when it was first announced by Fleischmann and Pons. They were hands-on experimenters and senior people whose results were not to be discarded easily. And then Scott came up with a concept. The big problem was, how could you possibly get nuclear reactions, and if you got them, how could they be free of radiation? And Scott came up with this concept that ions were behaving like electrons in this metal hydrogen system, and just struck me that that was the only possible explanation I could think of.
A key point. First, I should point out that I'm working on cold fusion as a consultant for Oakton International Corporation, not for the Naval Research Laboratory. During the early stages of cold fusion, they were very interested in it, as everyone was, and I did. They gave me enough freedom to explore these ideas, and then after a certain point, they couldn't justify funding it anymore. But there's an interesting point about this electron behavior that Talbot was referring to. The idea gets down to what they call band states, energy band states, which are particular things that are of importance for electrons and known to be important for electrons. And the basis of these things involves two things that are very important for metals and electrons, which is that, first of all, you're not looking at something, when you look at conductivity in metals or even in semiconductors, you're not looking at something that happens at high temperature. at high temperature metals melt. You're looking at really what is a low temperature type of behavior. You're seeing at room temperature something that becomes perfect at low temperature. And what I'm talking about is all metals, for example, that have sufficient periodic order at absolute zero have perfect conductivity. And what that means is you can't tell where the electrons are at all. And the interesting thing about hydrogen, when it interacts with palladium or these transition metal materials, is that they behave the same way. You can't tell where they are at all, and they would be perfectly conducting at temperature equal to zero. And the fascinating thing about that is it's a very different picture than what one has at high temperature, where you can see where where the things are happening. And so we put forth, as Talbot was saying, I suggested this idea, and the thing that came out of it immediately was that you weren't so much trying to force things together as you do at high temperature. You were sort of letting them happen. You were looking at what would happen at colder temperatures in something that is a well-defined solid. And by well-defined solid, I mean the same things that make electrons conduct well, which are things like having regular arrangements of atoms and having a well-defined structure. These things can come to work when these hydrogen ions occupy these energy band states.
Oh, I remember that on the TV when I heard it, they were talking about you could take a gallon of water and run your house for a year on that, and that was the potential if this was true. I mean, do you all both believe this is still possible?
I certainly believe it.
I do too.
Yeah.
Well, they were also talking about, there were a lot of scientists are saying, well, it was probably some kind of a chemical reaction, it wasn't nuclear. Now, how do we know that it was nuclear? Now, have you been following what's going on over the world, too? And how's the progress on these?
In fact, that's the key point. That's part of the reason that people had such a hard time believing that cold fusion was real. In order to have a nuclear reaction, you have to create some new element. And it turned out that people were looking for what you might call the vestiges or the residual of the creation of the element that one knows of at high temperature.